In the last video, we talked about the idea of what entropy is, and now we're going to look at absolute entropy. In other words, a way that we can actually quantify the entropy of a substance, and therefore quantify the entropy change as a reaction is taking place. Let's do a little review here. The first law of thermodynamics says that the total energy in the universe is constant, which means that for a system, any change in energy is only a result of energy transfer in or out through heating, or energy transfer in or out through working for that system. The energy that's transferred through heating is the enthalpy change, and working is pressure times the change in volume. So we could also restate the first law of thermodynamics as delta E for the system is delta H plus P times delta V. The second law of thermodynamics says that the entropy of the universe always increases every time there's a spontaneous process. So that means if you add together the entropy change for the system and the entropy change for the surroundings, that sum has got to be a positive number. We'll come back to this basic idea in a subsequent video to help us determine when reactions are spontaneous and when they aren't. The third law of thermodynamics we can get to by considering a pure crystalline substance in its solid state. So that we're talking about a solid here. It has particles that are in the lattice, but they're vibrating if they're at high temperature. And so there are a bunch of microstates that are possible due to that vibration. As the temperature lowers and the vibration becomes less pronounced, there are fewer microstates. If you can drop the temperature all the way down to absolute zero, then there is no vibration anymore. And so we go from more microstates to fewer microstates to finally at absolute zero, 1 microstate. Now remember that the entropy of a system is equal to the Boltzmann constant times the natural log of the number of microstates. And if you have 1 microstate, then the natural log of 1 is 0. So that means the entropy, when you're at absolute zero for a pure crystalline substance, is 0. And that's the third law of thermodynamics. For a pure crystalline substance, the entropy of the system is 0 when you're at 0 kelvins. Next, let's take a temperature approach to entropy change. There was a flurry of activity at one point in history as physicists and engineers were studying engines, and they started to discover some things that led to a deeper understanding of entropy and energy transfer through heating. Imagine you have this situation. There's a system. The system is some gas. So there's some gas, and it's trapped in this tube underneath this plunger. It's sealed in there, can't escape. The plunger is held down by a bunch of very tiny grains of sand. And this whole thing is immersed in a water bath that's very large. And so that means the water bath has a constant temperature because there's so much thermal mass there. What happens if we take out one tiny grain of sand off the top of that piston? What will happen is the system will expand. If the system is expanding, that means it's losing energy through working. So there's a loss of energy to the system. That energy loss will be made up for by a small transfer of energy through heating into the system. And if you continue to do this, little by little, taking out grain of sand after grain of sand after grain of sand, what will happen is the volume will slowly get larger and larger and larger, but it'll do this infinitely slowly. This is what's called a reversible expansion. Imagine putting this on a graph of pressure and volume. On a graph of pressure and volume, this would look like this. The volume is getting larger, the pressure is decreasing as those tiny grains of sand are being taken out one by one, and this very slow expansion takes place. So in addition to the volume changing, energy is being transferred into the system through heating at this temperature. That curve is just a segment of a larger curve that represents a constant temperature on this pressure volume graph. If the temperature were lower, the same kind of expansion would happen, but the energy that would be transferred in there would not be the same quantity. A guy named Carnot found that the ratio of the hot temperature heat transfer to the hot temperature was going to be equal to the ratio of the low temperature heat transfer to the low temperature. He realized that this ratio represented the change in the dispersal of energy as the particles expanded. Or another way of thinking about this is this represented a change in the usefulness of the energy from that which could do work expansion to that which could not do work, which is another view of entropy. And so the change in entropy during this expansion is equal to the total energy added through heating in this reversible expansion divided by that temperature. And that's that ratio that's going to be the same at the hot temperature and the low temperature. So when the heat transfer is positive and the entropy change is positive, then that means if the temperature is low, there is a larger entropy change than if the temperature is high. Now, this general argument that we're making here, you don't have to do any real calculations or anything with this. It's just meant to make you aware that it is possible to use measurements and calculations to find the entropy change associated with raising the temperature of a pure substance to a standard value from absolute zero, and therefore you can know the entropy at some standard conditions. If those are standard conditions, then these are called standard molar entropy values. Now, in reality, understanding how to do this is way beyond the scope of this course. If you take physical chemistry in college, one of the hardest classes in undergrad chemistry, you will take a much more rigorous approach at understanding this. In fact, what they do is they integrate the ratio of the function that defines constant pressure heat capacity and absolute temperature from 0 kelvins to standard temperature. You don't have to worry about doing that. That's way past the scope of this course. But the bottom line is we can know that it is possible to, starting from absolute zero, where S is 0, figure out a change in the entropy of the system by looking at temperature change and energy transfer, and adding that change to 0, come up with what is actually the entropy. So unlike the other state functions where we're only interested in changes, we can actually know the entropy of substances at a given temperature and other conditions. So we come to the idea of standard molar entropy. The standard molar entropy is the entropy of 1 mole of a substance under standard conditions. Here are the standard conditions: 298 kelvins, so that's approximately room temperature, 1 atmosphere for any gases that are involved. If there's a solution, its concentration is 1 mole per liter. And for any solids or liquids, we're talking about the pure substance in its most stable form. So what we mean by that is, for example, carbon comes in a few different forms. Diamond and graphite are 2 of them. Graphite is more stable than diamond, so that's the form that would be associated with standard molar entropy. You can look those values up in tables. They've all been figured out for lots of different substances. And the value of this is that we can use a formulation very much like Hess's law for enthalpy change to figure out what is the entropy change for a reaction or a physical change. So what it looks like is the change in entropy is equal to the sum of the standard entropies of products, and they're mole adjusted because they're all going to be reported on a per mole basis. That's why the N is there, minus the sum of all mole adjusted standard entropies of reactants. So let's do one example problem here. What's the entropy change associated with the combustion of propane, which is C3H8? So let's write the chemical equation. It's C3H8 is reacting with oxygen. It's going to produce carbon dioxide and water. A 3 here balances carbon, and a 4 here balances hydrogen. And then we'll have 10 oxygen on the right, so a 5 here balances oxygen. If you look up in a table the standard entropies of these substances, you will find out that for C3H8, that value would be 270.3, and the unit here is joules per mole Kelvin. That's going to be the same unit for all of these. Oxygen is going to be 205.2. Carbon dioxide is 213.8 joules per mole Kelvin, and water is 188.8. So the entropy change for this reaction is going to be 3 moles for the carbon dioxide times 213 joules per mole Kelvin plus 4 moles for the water times 188.8 joules per mole per Kelvin minus, now we're in the reactants, 1 mole times 270.3 joules per mole Kelvin plus 5 moles, this is for the oxygen, times 205.2 joules per mole per Kelvin. When we calculate this all out, we get 100.3 joules per Kelvin. And when you think about entropy being the ratio of a Q to a temperature, that unit makes sense because we would measure energy in joules, we would measure temperature in kelvins.